Welcome back, everyone. In this video, we'll talk about sampling, error, distributions, and the Central Limit Theorem. We'll begin by talking about sampling error and degrees of freedom. We'll then move on to the Central Limit Theorem, the concept of the sampling distribution, and standard error. Let's think back to reasons 2 and 3 for statistics, as we discussed in our last video. Reason number 2 is that statistics allow us to take data from a sample and generalize or make inferences about what might be happening in a population. Reason 3 was that statistics are mathematical techniques that help us to separate the unsystematic variability, the effect, in our data, from the unsystematic variability, or error, in our data. Drawing conclusions about populations based on samples is always going to involve error. Representative randomly selected samples are part of the solution. But we also have a set of statistical concepts that are aimed at tackling this sort of error. Sampling error refers to the difference between a given sample statistic and its corresponding population parameter. Representative and randomly selected samples tend to approximate the population that they were drawn from, but there's still always going to be error. How can we account for this error? One approach is to adjust how the statistics are calculated by using degrees of freedom. Let's talk a little bit about calculating standard deviation. How we calculate standard deviation changes depending on whether it's the parameter or the statistic. On the left, we see the formula for population standard deviation, and we can tell just by looking because the standard deviation is represented by sigma and the mean is represented by mu. N represents the size of the population, in other words, the number of x's. That bit in the top half of the fraction is the sum of squares. Dividing by n gives the population variance, and taking the square root of that gives us the population standard deviation. On the right, we see the formula for sample standard deviation. Notice that it's almost identical, except that both the mean and the standard deviation are represented by English letters, and that we divide by n-1, also known as the degrees of freedom, instead of by n. Why is this the case? Remember that we want an unbiased estimate of the population standard deviation. It doesn't have to be perfectly accurate, but it must not consistently over or underestimate the population parameter. Dividing by n would mean that our sample standard deviation would consistently underestimate the population standard deviation. In other words, our estimate of the standard deviation based on the sample would always be slightly smaller than the true population standard deviation. And this is because samples, in general, have less total variance than the populations that they're drawn from. The good news is that we can simply divide by degrees of freedom, n-1, to adjust for this fact. But what is degrees of freedom, and why n-1? Degrees of freedom refers to the number of unique pieces of information in your data. In other words, the number of scores that can freely vary. In the case of standard deviation, this means how many of the data points do I need to tell you before you can accurately calculate standard deviation? Your first reaction might be all of them, but actually you only need n-1 data points. As an example, imagine that your average score across 4 quizzes is an 8. Your scores on the first 3 quizzes could be absolutely anything. Let's say that you got a 10, a 7, and a 6. However, in this case, your score on the last quiz must be a 9, because this is the only score that will give you an average of 8. Thus, in this example, your degrees of freedom are 4 minus 1, which is 3, and notice that this is n-1. If this is a little confusing, don't worry about it. Just remember, the degrees of freedom for sample standard deviation is n-1, and that using this correction ensures that the sample standard deviation doesn't underestimate the population standard deviation. I'll note briefly that the exact value of degrees of freedom differs for different statistics. Sometimes it's n-1, sometimes it's n-2, but the value is always the number of pieces of information you need to calculate that statistic. So we've seen how using degrees of freedom when calculating sample standard deviation helps us avoid underestimating population standard deviation. But how else can we account for sampling error? There are three concepts that will be useful to us here. The first is the central limit theorem. The second is the concept of the sampling distribution. And the third is something called standard error. Let's discuss each one in turn. The central limit theorem is a theory for approximating the population mean, mu, using samples. If we draw a sample from the population, plot the mean of this sample, throw this sample back into the population, in other words, sampling with replacement, then draw another sample and repeat this process, we will create a distribution of sample means known as the sampling distribution. So, just to reiterate, the sampling distribution is the distribution of the means of the samples that we pull out of the population. The mean of the sampling distribution is our approximation of the population mean. According to the central limit theorem, the more samples we draw from the population, the closer the mean of the sampling distribution is to the mean of the population. Thus, the sampling distribution is a distribution of sample means arranged around the population mean. The standard deviation of the sampling distribution is called standard error. This is an estimate of the amount of error involved in our estimation of the population mean. Standard error tells us how much error to expect between our sample mean and the population mean. As far as making inferences goes, the smaller the standard error, the better, because this means that our sample mean is a better estimate of the population mean. So how can we get a smaller standard error? Standard error, as we see in the equation here, depends both on the standard deviation of the sample, represented by s in the numerator, and the size of each sample, represented by n in the denominator. So, a smaller standard deviation is good, and we can get this by doing everything we can to reduce unsystematic variance. Simultaneously, a larger sample size is also good, and we can do this easily just by involving more participants in our research. Both of these will result in a smaller standard error, and thus a more accurate estimate of the population parameters. So the more we sample our population, the closer the mean of our sampling distribution will be to the population mean. However, we don't necessarily need multiple samples. What we need is one large, randomly selected, and representative sample. Recall that the aim of the sampling distribution is not to recreate the population distribution, but to approximate the population mean. The standard error estimates how different our sample mean is from our population mean. The smaller it is, the better our sample mean approximates the population mean. So let's walk through an example. Let's say that our population is UCSB students, and we're interested in measuring their happiness with online learning. Let's say that our population mean, mu, is 4.29 out of 5, our population size, n, is 25,000, and our population standard deviation, sigma, is 2. So we'd end up with a population distribution that looks like this. Recall, of course, that in real life we would not be able to know all of this information about our population. So now, I'm going to draw a series of samples from this population with replacement. Each sample will consist of 100 students. In other words, n equals 100. So, from our population, I draw a sample. I find the mean. In this case, our mean is 3.96. And I then throw it back in the sample, having recorded that mean. I now draw another sample, calculate the mean, 4.32, throw it back into the population, pull out another sample, calculate that mean, 4.04, throw it back in the population. I do that again, calculate our fourth sample mean, throw it back, and finally get our fifth sample of 4.2 and throw that back into the population. Now, I take each of those means and plot them as a point on a distribution. If I continue to do this over and over and over again, we'll eventually create a distribution that is normal, even if the original distribution wasn't, and the mean of this distribution will be our best estimate of the population mean. So, we've covered a lot of ground in this lecture, and I want to take a moment to recap. Our goal here is to approximate population parameters from sample statistics. In order to do this, we need to know how accurate our approximations are. The Central Limit Theorem tells us that if we draw many sufficiently large samples, in other words, samples of 30 or more data points, and create a distribution of these sample means, in other words, a sampling distribution, the sampling distribution will be approximately normal even if the population distribution was not. The standard deviation of the sampling distribution will give us the standard error, and the mean of the sampling distribution will be our best estimate of the population mean. I'll close by noting that it's important to recognize the difference between distributions and sampling distributions. In ordinary distributions, each data point is one value from the sample, for example, one student's score on a test. In sampling distributions, each data point is the mean of one sample drawn from the population.